Good afternoon. I'm Arlindo Silva from NASA Goddard. It's a little switch gears here. We're going to be talking about biomass burning in global models, and in particular, the specification of smoke injection height. I'm going to give a brief overview of the GSF mini reanalysis during CCARs and some assessment of the vertical structure of the aerosol extinction. And why do you think we have a need for putting the smoke in higher level than we're doing right now? A quick overview of the Plume model and some sort of Plume calculations over CCARs over GSF, and I will conclude some remarks why we don't think that right now we have the right parameterization to address what we need. Let's move on. GSF is just a global model. The configuration I'll be running is just a global AGCM running at 25 kilometers globally on a cubosphere. Runs with Mianchin's go-kart aerosols built in and transported by the model and coupled to the radiation. No indirect effects in this particular circulation. So we use this version of GSF for several applications, for long-term reanalysis and for seasonal prediction, and as well as for day-to-day weather and aerosol forecasting, particularly in support of field campaigns. One of such campaigns that we supported was CCARs, and as part of that exercise, after the campaign, we go back and try to do a mini reanalysis for the period where we bring in data that was not available in real time. And at the same time, we do a comparison with in situ measurements and try to go through iterations of make improvements. So this run just uses our QFED daily biomass emissions for modes FRP. It has both the full meteorological data simulation, also aerosol data simulation with MODIS, MISR, and Aeronet, including the Dragon network was deployed at the time. So let's give you a quick assessment. I think Cynthia Randles gave a talk early this morning. She went a little bit more detail. But here is put together all the HSRL flights during the campaign, all of them string together. And you can see the occurrence of several major fires, like the so-called Oregon fires, the Colorado, Wyoming, and finally the rim fire. And here, typical comparisons of curtains of the diode HSRL backscatter in the model. You can see the model pretty much capture a lot of the right structures, but in cases such as this one, there's some elevated plume that things is not really well captured. One obvious reason for such behavior, of course, is that all the smoke is being deposited in the boundary layer, and therefore, if there is a strong plume injection, will be missed. But here's another example. The Colorado fires, where also we capture in reasonable well the vertical structure of the backscatter in this case. But there are a few of those plumes that are not elevated enough. But by and large, and here's for the rim fire where things didn't really reach very high. And in such a case, we're really so we like to try to find ways to implement a plumerized parameterization that will elevate those plumes they need to, but without really putting too much stuff up there. So here's our overall assessment of the model vertical structure. Here's backscatter GSF and dial. And you can see that the model has a little tendency to put a little bit too much in the free troposphere. Whatever we do, we don't want to really putting, on average, even more stuff up there than we already have. And here's another assessment of the GSF PBL height, also in collaboration with the HSRL group. And overall, we seem to have, during the CCAR period, about 500 meters or so, a little bit too high, boundary layer. So very few words about the quick fire emission data set, just based on FRP. Simply we estimate daily mean emissions, and those FRP emission factors have been tuned in such a way as to produce agreement with observed AOD over the globe. So it's basically we should call them actually perceived emissions that GS5 like to reproduce the AOD that's such absorbed. It's not really, in some sense, the real emissions, right? They are the perceived emissions. There are daily mean emissions, and in the model we prescribe a diurnal cycle derived from geostationary satellites. And in GS5 right now, as I mentioned before, all the emission is deposited in the boundary layer, and we rely on convective transport and whatnot to take the smoke out. So in order to investigate some of those fires, we go to our good friend, which is the MINX, the stereo height estimates from MISR, which is really the ground truth for most of these plume heights investigations. And we're lucky enough we got that from Tom Cosera and NASA Goddard from Ian's group. There will be about 90 or so of those biomass plumes that have been digitized, although MINX is a very nice data set, but really has to be done essentially in a manual, semi-automatic way. So we had about 90 plumes to begin with. And here I'm plotting it. This is a typical sort of distribution of heights you get for a plume from MISR. So we have here the mode of that distribution, and also 95% IO. And here I'm plotting against the GS5 PBL, presumed GS5 PBL in here, and here is the plume height. And you can see to a large majority of those plumes are in fact within the boundary layer. And several of them, the light blues are actually above. It's about 15% for those ones that were digitized. And the red here simply shows here the top of the plume, to showing the notion of extent. So we do have a few of those plumes that we could use a little help to bring it up. So we turn to the Freitas plumerized models, pretty good compromise between comprehensive physics and still being a implementable one-dimensional parameterization, which has basically a one-dimensional built-in cloud model, and includes entrainment by the lateral plume, including the effect of the horizontal wind in diluting. And you can, in the way it is parameterized, the entrainment, of course, decreases as the plume increases. The smaller the one, the more susceptible it is for dilution. And the model pretty much predicts the vertical velocity inside the plume, from which you can derive the maximum, the entrainment, and have sort of how you're going to distribute that mass. So in a way, you compare this maximum, this mass distribution to the mode of the plume in MISR. So it is driven, if you think about the main parameters you can get for remote sensing being the FRP or an estimate of the average size of the fire, you can compute a heat flux, a convective heat flux that needs to drive those buoyancies. And the surface buoyant flux scales as FRP, not the heat flux, actually, it's the FRP. And the surface, the radius of the surface relating to the area, and the boundary condition being basically the W at the surface is a function of this buoyancy heat flux by the square root of the area. So there's several implementations of the Freitas models, and results are all over the place, but most of them really you can trace back in how those basic inputs, the heat flux or the fire or the FRP, where I'm not going to go into detail. What I'm going to be using here is, is approach that's very similar to what Gonzalo did, where the fire you estimate from a dual band Dozier type of algorithm, and you take the FRP retrieved by modus. Those basically provide the inputs that you need. So I'm showing here a comparison between, for those 90 plumes or so, between what was observed and what was measured. It was modeled on the top. But I'm normalizing each one of this plume height by the perceived boundary layer height. And the reason is I'm interested in those points here, the ones that are actually above the boundary layer, right, where this number is above 1. And you can see that, in fact, there's a few of those plumes where both the observations and the model put in on that quadrant. A number of them in yellow here are the ones that are in the boundary layer. Those are, for modeling purposes, they're of no consequence. You don't really need to predict those very accurately, because once you put in smoke in the boundary layer, the diffusion in the model will mix them. So we don't really need to worry about those. But those are the worrisome ones, things that, in fact, nature is in, say this inside the model layer, and the plume height model is putting above, and those are the cases that we missed. That would be no harm done. That's exactly what we're doing by putting everything in the boundary layer. But those are the big concerns. So If you just plot this scatter diagram without any color, you cannot see any sort of relationship. But if you really focus on that's what really matters, and that's what the main concern. So you can try a lot of sensitivity to the radiative convector factors. You can look at the sensitivity to the fire area by using the Dozier or even a constant area. The results are not extremely sensitive to the fire size. What brings us the question, the plume height is a calculation that we have those surface drivers, the FRP and the sides, but also you have to specify an atmospheric profile in terms of T and E, right? That's basically your stability profile. And that usually comes from the model. There's not really much you can do at this time. So the question is, we could have a limitation due to that. So the question is, what's the best we can do for a given set of atmospheric profiles? We can try to get a sense of this question by doing the following, what-if experiment. To find the optimal, FRP or the area that match the estimates, right? So given that atmospheric profiles, can we minimize dysfunction and find the best agreement with the observations? So, and here's the results that you get. It's basically, I'm still prescribing the area using the Dozier approach, and here's that set of diagrams. A lot of those plumes here, they were in the boundary layer. You are able actually to lift them up and have a nice, but you still have a few residual ones that are supposed to be in the boundary layer. They're also being lifted. And those are a little bit of concern. As I told you before, already have enough smoke in the boundary, above the boundary layer on average. So, in those here, I really don't care because whatever I put in the boundary layer would have not much influence. So that's the case for which I had verification. But you can do this calculation now for all the fires over North America over a given month. And here is the PBL, and here is the actually the plume rise. Actually, there's a typo here. But you can see that a lot of that smoke is being deposited above the model layer. And here's for Terra, a little bit more well-defined for Aqua in the afternoon, where the fire tends to be stronger. And also for, you can test sensitivity to areas to convective parameters. Within reason, as you vary, any implementation of that with the profiles that we have, we tend to put way too much smoke above the boundary layer. Unless you really go to a very weak heat flux where you basically put everything inside, but again, you don't seem to be putting much above. So, in conclusion, doing CCARs, the justified mean reanalysis, it does a reasonably well job for a global model of reproducing the vertical structure of aerosols, but we have some elevated plumes here and there that we were not capturing. But also we tends to be on average a little bit too much on the free troposphere, and the PBL is a little bit too high, and you have explored the sensitivity of the Freitas plume rise model to address this. But even under ideal conditions where you do that inverse calculation, you still seem to put in more stuff. So you really, your batting average, to go in there is not that great. In a pure climate model, what you really don't really matter, you have to represent the variability, probably would be okay. But in a forecasting model, you really want to hit, those precise ones they made outside. So that's some concern. So I didn't report on that. We did a lot of work in trying to use OMPs, elevator aerosol index, and trying to find matches, and trying to have that together with overshooting tops as another alternative. And of course, for very strong, well-defined pyrocumulus, which are not easy to find, for the run-of-the-mill sort of those fires that I showed you before, we could not find anything that could really have a practical alternative to the plume rise modeling. So at this point, I'm not entirely giving up, but I'm not really, ready to jump in because at least for North America, that doesn't seem to solve the problem. It's an entirely different story about the Amazon. We have conditionally stable atmosphere, very shallow boundary layer. What really those plumes really need to be, almost everything needs to be taken out of the boundary layer. But over North America in the summer, it is a very different story. That's all I had.
Okay, thank you. Any questions? We have time for a brief question. Mike?
Could you go back to your comparison to the HSRL secret?
Tell me when I get there. Which one? Which one?
Or that,
That one? That one?
or that?
Huh?
The first one, go to-
That's the first one.
Yeah, that's the one. I noticed in the other two cases that where the comparison is actually much better, you don't have, as you mentioned, those elevated aerosol layers. And
Yep.
you don't have that laminar structure in the later time over there above the PBL.
Mhm.
Could you have some idea of the processes that are forming those layers in the atmosphere that are missing in the model?
Yeah, so my whole, premise for this is that, we do have we don't have a plume rise. You really have a strong fire that has enough, buoyancy that would, puncture, the boundary layer. So it's basically a plume rise, problem. So at this point, I haven't really gone back and done the case study to find out exactly, what that is. That would be my suspicion, that in fact was a strong fire that had enough buoyancy. And to represent that, we need a plume rise, parameterization.
Okay, thank you again.